Hey all, I'm Brian Kanhofer and I'm a software engineer with Syncopated Engineering. Syncopated Engineering is a creative solutions provider based outside of Baltimore, Maryland. We design custom hardware and software for wireless comms, signal processing, and machine learning for both the government and commercial spaces. Our portfolio includes the Cielo family of cognitive radio products and the Allegre edge analytics hardware and acceleration platform. Today I will be discussing our Mockingbird RF emulation platform from our Cielo family of cognitive radios.
An important element of cognitive radio is detecting and reacting to other signals found in the operating band of the radio. When testing a cognitive radio or other communication system, it is useful to emulate the RF spectrum so it resembles the environment where the radio will be deployed. Using our Mockingbird RF Emulator, we can generate rich RF scenes composed of many different waveforms. An RF scene in Mockingbird consists of a set of waveforms and traffic patterns. A waveform is the actual IQ samples to transmit, and a traffic pattern describes how the signal is to behave. At its most basic, the traffic pattern describes the on and off characteristics of the waveform. GNU Radio, SigMF, is a flexible mechanism for sharing recorded signals between signal processing systems and engineers. SigMF defines dataset and metadata files to allow for the portable transfer of signal processing data. In the flow graph, you can see an example of the generation of a complex sine wave. In this case, we are outputting complex float 32, but we support complex integer types as well. The SigMF block we are using here is available open source on GitHub. The baseband IQ files generated can be directly imported into Mockingbird. As a quick demonstration of Mockingbird, we have used GNU Radio to generate some custom IQ baseband signals to use in an RF scene. We will then show the outcome by reading the output back into GNU Radio using a Lime SDR. The scene we are generating consists of a set of signals that one would expect to see outside of an airport. ADS-B is a periodic broadcast signal in the UHF band that is sent by an aircraft to indicate aircraft identification, velocity, location, or altitude. This will be active anytime an aircraft is in the vicinity of the airport. AM analog voice is found in the VHF band and consists of voice chatter between the aircraft and the tower. We would expect this to be most active when an aircraft is preparing to taxi and take off. The primary radar is a pulsed radar system operating in the S-band. We would expect this signal to be visible as a periodic sweep as it scans the surrounding airspace. Back in the waveform section of the Mockingbird web app, we have preloaded all of the signals required for our scene. We have ADS-B signals for 3 planes at 3 different power levels to model different ranges for each aircraft. For this demonstration, each plane will only be sending a single message twice per second. We have a pulsed radar at 2.8 gigahertz running at 5 times per second to model the primary surveillance radar. We are pulsing our internal sine wave generator for demonstration purposes here. Ideally, we would load a custom baseband IQ representing a sweep or add a new radar generator to Mockingbird. Finally, we have 2 AM voice signals at 120 megahertz to represent the aperiodic communication between aircraft and the tower, both with a different pattern of life. Once we start each of the signals, we can observe the signals in our spectrum analysis flow graph using a Lime SDR. To show the emulated RF spectrum output, I have connected a Lime SDR to our Mockingbird system. Then I am using Phosphor to show the spectrum. The first band we are looking at is the AM radio band. To make it a little bit more interesting, I've added a couple more transmitters on a couple simulated channels. For each transmission, we have adjusted power levels to simulate aircrafts at different ranges. In the S band, we can observe our model for the pulsed radar. Each long pulse of the radar would represent a single sweep of the system. As mentioned before, we would better represent this signal using a custom baseband representation so we can show the individual pulses during each sweep. The last band we're going to look at is the one containing ADS-B broadcasts. In this band, we can see the periodic bursts sent from the 3 simulated planes at 978 megahertz, each at a different power level to demonstrate different ranges. Together, all these generated signals, the pulsed radar, analog voice, and ADS-B, could be the basis of an RF test environment for SDR algorithms. The signals we have chosen span several different bands, but a user could certainly generate a more useful RF environment that would focus on a single band.
We're continuing to improve our RF emulation capabilities, and we would love to hear about some application ideas that you may have. We are always looking for unique problems to investigate in the RF space. To find more information about Mockingbird and Syncopated Engineering, please go to the link below. You can find us in the Syncopated chat room all this week if you have any questions about Mockingbird, our demo, or if you want to just discuss RF emulation in general. Thanks for watching our talk.